I think you're really going to enjoy this lesson today because by now this should all be really old hat to you. So we're going to apply what we already know about transformations of polynomial functions, or of functions, and apply it to polynomial functions. So our question is, how can we apply our knowledge of transformations to polynomial functions? And we're going to apply transformations to graphs and then apply this information to modeling power functions. So the transformation of y equals x cubed was an equation of the graph of y equals x cubed under a vertical compression by a factor of 1/2, followed by a reflection across the x-axis, a horizontal translation 3 units to the right, and then a vertical translation 2 units up. Okay, so we're going to use x cubed as our base. If we want to compress by a factor of 1/2, then we need to multiply by 1/2. So that'd be 1/2 x cubed. And then we want to reflect across the x-axis, so we need to multiply by a -1. So that makes it a -1/2 x cubed. And then we want to a horizontal translation 3 units to the right. So we want to move it right, so we need to do the opposite. And we need to do x minus 3. And then translation up 2 units, we add the 2 on to the end. So there you go. Y equals -1/2 x minus 3 cubed plus 2 is all of those things. So all the same rules apply to cubed powers as it did to square powers. Okay, why don't you go ahead and take a minute and do this one. What's an equation of the graph of y equals x cubed under a vertical stretch by a factor of 2, followed by a horizontal translation 3 units to the left and a vertical translation 4 units down. Okay, go ahead and pause your video, write it down. I'll write it down in just a second. Alright, so if we have a stretch of 2, so y equals 2, and then your x, we want to move it 3 units left, so we need to do plus 3 cubed, and then 4 down, minus 4. There's your equation. Easy peasy. Alright, we're going to find the zeros of a transformed cubic function. So if a, h, and k are real numbers and a is not equal to 0, how many distinct real zeros does y equals -a times x minus h cubed plus k have? So in order to figure out how many real solutions we have, we need to solve for x. So the first thing we need to do to solve for x is to go ahead and set it equal to 0. Then we're going to subtract k from both sides, and then we divide by -a. So we have x minus h cubed equals k over a. Now to get rid of that cubed, we need to take the cubed root. So we take the cubed root of both sides. You get x minus h equals the cubed root of k over a. And then you have to add h to both sides. So our possible solutions are only one. We can only have one real solution for this one because it's negative. Alrighty. Okay, given 2 real zeros, what is a quartic function? So that means which power to the 4th with only 2 real zeros, x equals 5 and x equals 9. Well, if we know that we have 2 real zeros, that means we can write those as our factors. So we can start by using transformations, and we find a quartic function with zeros at positive and -2. And then we do a translate down 16 units to find that difference. So we have x to the 4th minus 16. That'll give us solutions at positive and -2 because 4th root of 16 is 2. And then 9 is 7 units to the right of 2. So then we translate that 7 units to the right. So how do we translate to the right? We take and put that in parentheses, minus 7. Oh, there you go. And then that's a function. Isn't that exciting? You guys just made a function. So that is one way in order to find zeros. Another way is to use the algebraic method. Oh, I forgot to tell you on this one. The reason why we did plus or minus 2 is because we needed to find the middle of the 2 points. Sorry, I didn't explain that very well. So between 5 and 9, we had to find the halfway point. Halfway is 7, and 7 is 2 away from 5 and 2 away from 9. That's why we needed to find zeros at plus or minus 2 so that we could take this function and translate it down and over so that it would fit this model. My apologies. Okay, so the second method we're going to do is to use algebra. So we know that our zeros are 5 and 9, so we can set those as our two factors, x minus 5 and x minus 9. And then we're going to multiply that times some polynomial that we don't know, because there has to be how many solutions for a quartic? There has to be 4 solutions. If there's only 2 real solutions, that means 2 of our solutions are imaginary, but we don't have an equation for that. So we're just going to say that x of q is a quadratic with no real zeros. So why don't we just go ahead and do the most basic one. If we just say I and negative I, so that's x plus I and x minus I. When you factor it, you get x squared minus xi plus xi minus I squared, which is negative I squared equals positive 1. So that's how I got this, x squared plus 1. I just multiplied by the two simplest imaginary solutions. Okay, and then we just go ahead and we multiply that out. So we expand our binomials, and multiply again. You get x to the 4th minus 14x cubed minus 46x squared minus 14x plus 45. And that's just from multiplying all those together. When you multiply a binomial times a trinomial, you multiply all these on the top by the first one and all these on the bottom by the second one. And then you add all of your like terms together, and you will get this. Okay, so choosing either method that you like, what is a quartic function, f of x, with only 2 real zeros at x equals 0 and x equals 6? I want you to go ahead and do this as your lesson check with your partner, and then just check each other's work and make sure that whether they did it graphically by translations or whether they did it algebraically, that they were following the same basic principles that we've been using. Okay, for our vocabulary, a power function is a function of the form y equals a times x to the power b, where a and b are non-zero real numbers. So for example, 0.5 times x to the 6th is a power function because we're taking 0.5 times x raised to a power. And these are all just various power functions. The constant a is the constant of proportionality. We're going to be using that. So for modeling with a power function, we have a wind farm with a source of renewable energy found around the world. If you've never seen a wind farm, they're pretty cool. They're also very, very, very tall. The power P in kilowatts generated by the wind turbine varies directly as the cube of the wind speed in meters per second. So this picture shows that the power output of one turbine at 1 wind speed to the nearest kilowatt. So when the wind is going at 8 meters per second, they're producing 600 kilowatts. So to the nearest kilowatt, how much power does this turbine generate at a 10 meter per second wind? So we're going to be making a proportion. So 8 meters produces 600 kilowatts. How much does 10 meters per second produce? So we're going to use our power formula, so A times V cubed. So from the picture, we get our power is 600 when our wind speed is 8. So we just need to solve for A to give us our proportionality. So 600 equals 512A. You get that from cubing 8. And then you just have to divide by 512. And you get A is about 1.1719. Okay, when you know what that A is, you can plug the A back in. And then we wanted to find when our speed was 10, so we plug in 10 for V. And you just plug in 10 cubed is 1,000, so multiply that. And there you go. You get 1,171.9 or 1,172 kilowatts of power when it's 10 meter per second wind. All right, and then here's another one that's just like it. And I will assume that you guys can do it, but if you'd like to, you can go ahead and try this one as well. I'll go ahead and throw up the answer here really quick. Alright, so here's all the work laid out. So you just put in the 12 and the 210, you solve for A, you plug A back in, solve for the 20 to find your power. I got 972. Alright, we're done. Your homework is lesson 5-9. Make sure you compare your equations with your partner when you get to class. Have a great night.